안녕하세요.
안녕하세요.
안녕하세요. 예. 한 3분 늦었는데
안녕하세요.
죄송합니다. 아침 일어나는 게 쉽지가 않네요. 19분. 출석만 하고 그냥 바로 시작할게요. (3월 26일) 네이버 분들은 다 오셨고 학생들만 기다리면 되나요? 네. 뭐 더 기다릴 필요는 없는 것 같네요. 예, 그러면 시작하겠습니다. Okay, we'll get started. Let me just share my screen. Yeah, okay, I'll just share my screen. And before we get started, I think there were some questions in Classroom. So we'll check. Right. So Sungwoo Kim said he can't download the Dropbox link. Is that still a problem? Sungwoo? Is he here today? Wait, is he a student or a neighbor engineer?
Actually, I'm from neighbor. Actually,
Okay.
it's okay in this morning. But I started download about 10 minutes ago.
Okay.
I think there was a bit of problem yesterday.
Okay, cool. And Junie Kang said he can't decompress CSV. So is that still a problem, Junie Kang? Junie Shi? I think he is here. 준이님 혹시 아직도 이거 그 압축 푸시는 거 문제 있나요? 아직 못 풀고 계십니다. 그 첫 압축은 푸신 거죠? 그러니까 이제 그 테이블 잔뜩 나오기 전, 네네. 그럼 그 건집으로 해도 안 되나요? 건집하고 뭐가 있죠? admissions, CSV, gzip. 네, 이런 식으로 하면 안 풀리나요? 윈도우. 아, 윈도우면 앞으로 굉장히 불편하실 텐데. 파이토치는 텐서플로우가 윈도우에서 되던가요? 아, 네, 그렇죠. 리눅스가 가장 적합하죠. So what we're saying now in Korean is that the Linux will be the standard environment for all our projects and homeworks. And someone is having problems trying to decompress the file that I uploaded on Dropbox in the Windows settings. So we're having a problem with that. 아, 파이토치가 윈도우가 있긴 있군요. 반드시 윈도우가 안 되네. 이게 압축을 풀면 36기가나 돼가지고 제가 올리기가 쉽지가 않을 것 같거든요. 네, 압축하면 이제 6기가인데 압축 풀면 아마 한 40기가쯤 40기가 넘을 것 같은데 한참 올려야 돼가지고 준이님 혹시 리눅스 환경 아예 그 준비가 안 되나요? 네, 네이버에서 요거 이제 수업 듣는 분들에게 따로 이렇게 뭐 가상 환경이나 이런 걸 제공을 안 해주나요? 아니면 GPU 하나씩 준다든가 뭐 이런 거 전혀 없나요 지금? 이거 앞으로 이제 딥러닝 모델 같은 거 트레이닝 학습하려면은 GPU도 하나씩 있어야 될 텐데. 아, 우리 학과에서 주려나? 네, 아직 제가 이제 오늘까지 이번 주까지는 이제 약간 제가 설명 위주로 하고 다음 주에 숙제가 나갈 거거든요. 이제 이 데이터를 직접 다루는 숙제가 나갈 건데 그때까지 제가 우리 학과 차원에서 이제 GPU가 준비가 되거든요. 서버가. 그거가 여유분이 얼마나 있는지 모르겠는데 제가 한번 알아보도록 하겠습니다. 그게 안 되면은 아마존 AWS를 쓰던가 그래야 될 것 같네요. So those of you who don't have those of you who don't have Linux system in their hands, so the grad school of AI has procured a bunch of set of GPU servers. I'm not sure how if everybody can use this in this class because we have a lot of classes in this semester and probably hundreds of students are attending the class. So I'm not sure if we have enough GPUs to go around every single student, but we do have hundreds of GPUs as far as I know, and I think they're in the process of being ready to be distributed to students and faculty. So I'll look into that and then see if we can, if I can give access to all the students in this class. And as I said, there won't be any homeworks or projects this week. So this week it'll be just me doing demonstration and explanation. I will try to. So the next week there will be homework doing kind of a pre-processing on the data set, and it'll be best if you do it in the Linux system because of all the. I guess we're going to use Python, so it doesn't really matter if you're in the Windows system or the Linux system, but. But yeah, but I recommend using mostly Linux, especially Ubuntu. So because I think PyTorch and TensorFlow both are probably packaged to be distributed to. I mean, Ubuntu is always one of the major flavors of Linux. So if you have Ubuntu system in your hands, it'll be better. If not, I'll try to find a way, try to get a bunch of GPUs so I can give access to everybody. All right, so let's get started. Okay. So last time we stopped after the SQL query demos. Oh, by the way, has anybody was anybody granted access to Mimic 3? Did anybody hear from the MIT PhysioNet? 혹시 액세스 받으신 분 있나요? 그때 2주 기다려야 된다고 그랬는데 혹시 지금 누구라도 뭐 그랜트 받으신 분 계신가요? 아무도 없으신가 보네. 네, 그러면은 SQL 쿼리 데모는 아마 다음 주쯤에는 조금 더 해볼 수 있을 것 같네요. 네. 네. 뭐 SQL 쿼리 뭐 굳이 안 해도 되니까 네, 넘어가겠습니다. 네, 그래서 다음 네. So the next topic is claims data. So I'll just okay. So as I said, so Mimic 3 is an electronic health records consisting of ICU records from Beth Israel Hospital. So it's a rich data set. It has the times, it has all the demographics, it has the medications, procedures, diagnoses, the lab measure, the lab tests, what else? The notes as well, and the continuous. So lab tests being like blood pressure or allergenic responses, or you're taking urine samples and analyzing your urine samples, all kinds of like lab tests. So it's a very rich data set. Compared to that, there's another medical records called claims data, and some people don't really understand the system, how the medical system operates on the national level. So I'll just briefly go over what claims data is, or how claims data is generated. So this is us, the patient, and we go to hospital and talk to a doctor. So this is a doctor patient situation, and the patient says, I have headache. Doctor says, take this prescription. So this is a one outpatient event. So compared to inpatient event, where you need to be admitted to the hospital and stay there for like a couple of days. As I said, outpatient encounter is a one-shot thing. So you go to hospital, you talk to a doctor, and then you get some kind of like treatments, and then you leave. It's a one-day thing. So this here is a outpatient encounter, and the doctor gives like a diagnosis, like, okay, this patient has a headache, and this patient has a fever or whatever, and then I will prescribe this patient a set of medications like Tylenol, ibuprofen, whatever. So that's that. And then after the patient leaves, the doctor will draft up a report that says like, this is me, and the patient was Mary. This happened on September 10th. The diagnosis was headache, and the prescription, which RX means medication. So prescription, I gave her a Tylenol. So this is like a claims report. So this is a claims report, and then the doctor submits that report to National Insurance Review and Assessment Service, or I think in the United States it's called CMS. Let's see. Yes, it is. So CMS takes care of Medicare and Medicaid, which is called like Obamacare. So in United States, CMS does this review. In Korea, 건강보험심사평가원, 심평원, basically 심평원 does that. So the doctor submits the report to 심평원, and the 심평원 reviews the report and see if there's any anomaly, if there is any incorrect inputs, or if sometimes like doctors try to like, do a scheme, so which means a 보험 사기, so 보험 사기, like insurance scheme. So they try to do that, like they fill like a fake input, or they try to like put some very expensive treatments that which the doctor didn't prescribe, but says on the report that they did, so they can get like a reimbursement, a big reimbursement from the government. So that like sometimes happens. So 심평원 will go over the report, claims report, and see if it's legit, if it looks good, and then if it looks good, here's the payment. So the 심평원 pays the money to the doctor. So everybody's insured in Korea. So this person can't be married. Like this Korean woman will have paid a very small amount of money because she is insured and like being diagnosed and getting prescription it takes like, I don't know, it costs 10,000 won or maybe 15,000 won, like 15,000원. That's it. But that is not the actual cost, because the actual cost is covered by the insurance, and the doctor needs to be paid back for the difference between the actual cost and what the patient pays. Because if we say that the actual cost was like 50,000 won, 5만 원, and the patient paid only like 10,000 won, 만 원, then the 4만 원, the 40,000 won is covered by the insurance. So 심평원 has to look at the report, the claims report, the gray thing, and then pay the difference to the doctor, the 4만 원. Or I don't know all the details of like insurance and how everything works. It depends on, it varies from like country to country, but as far as I understand, this is like basically the workflow of how like insurance claims and reimbursement is operated. So claims report is very is not very, but it's simpler compared to EHR. EHR has all the like lab reports, the notes and all that, but the claims report has a less amount of like information, less variety of information. So in case of Korean claims data, this is typically what the doctors will fill out. So you can see the table here. It contains provider information, provider being the service provider, the doctor, or it could be like a nurse. If you go to like a caretaker's home, like 요양원 is still a medical facility. So then the service provider there will be 요양사, and they're not necessarily doctors, but they're still providers. So provider information. So you see that here what it says in Korean is 진료 형태, means it's the type of encounter or type of like service, and it says 외과의뢰, so it's an outpatient encounter. And patient information, like the names and the birthdays and the insurance number, the 주민번호, whatever. Diagnosis codes. So is there a diagnosis code here? 상병명 및 부위. So this is diagnosis code. So why the patient came to the facility. It says 협심증. I'm not sure what 협심증 is in English. It's something to do with your heart. Kidney failure. So those two diagnosis codes and treatment codes. So what this doctor prescribed is not shown here. It's probably somewhere in the like the below area. And then the billing information, of course, like how much the patient paid and like what kind of insurance plan the patient had and all that. So it's not as rich as EHR. It says no notes, no lab results, no chart, because no charts. Yeah. So this is typically what it is, what it looks like to have a claims report. And so it can be, so claims report, due to the government policy, like government 2.0 or whatever, the policy where the government is supposed to open their data set, like the traffic data set, the financial data set, whatever data set. So according to the policy, open data policy, you can obtain from HERA. HERA is the 심평원, and so it's here. Like why can't I can click this. All right, I can click here. I can go here, and it says, so they open source E100. So this is inpatient data set. This is all patients. This is old patients. This is kids, the children. So pediatrics, basically. So they open source 4 types of data sets, and they're not EHR. They're still claims data. This is claims data coming from 심평원's some kind of like big data open source project. So the problem is it's not free. So it is not free. So it costs you $300. Well, not 300. It's 30만 원. So 300,000 Korean won per year. So if you look at here, the inpatient data set covers from 2009 until 2016. So it's about 7 years worth of data. And per year, you need to pay 300,000 won. So it's not cheap. So basically, it's not free. And the worst, what makes it worse is that the patients from 2 consecutive years are not linked. So patient record from 2009 and patient record from 2010. I mean, the claims report from 2009, claims report from 2010. Even though they're like consecutive years, they're not linked. So they don't consist of the same patient. So the HERA, the 심평원, have randomly sampled from the entire Korean population to construct a single year claims data. So like 2009 claims data, 2010 claims data, they consist of different sets of people. So it's not longitudinal. So you can't do like a long-term analysis. So basically it's not that good. So it's okay for like a single year analysis. Like if you wanna analyze what the most popular disease was per year, for example, like you can say in 2009, like fever was the most popular disease, and 2010, like I don't know, like headache was the most popular disease. Like you can do that, but you can't do like a per patient analysis on a longitudinal, like temporal level. You can't do that. So all our projects, I mean, if you're like really enthusiastic about claims data analysis or population, so what makes it like what differentiates between the claims data and EHR is that EHR data comes from a single hospital, so it's pretty local. Like I don't know, Bundang Seoul National University Hospital will consist mainly of patients from like Gyeonggi-do or Seoul, but it won't contain patient records, patients from like Jeollado or Gyeongsang-do. So it's local, but claims data, this is national insurance claims data, so it will consist of, theoretically, it'll consist of all the like Korean citizens. So if you want to do population level analysis, then there's no other way than actually looking at claims data. So some people say the claims data is like really not worth it because it doesn't contain like lab reports or charts or notes, but yeah, but I think there's some value to it. So all right. Yeah, this assignment was on old news. So yeah, all right. So this is the end of claims data. So from moving forward, all our examples and all our homeworks projects will be based on Mimic3, not claims data, because claims data I can't. Yeah, I don't want to buy claims data paying 300,000 per year. This is not really worth it. All right. So before we move on to the third class, any questions so far? Any question regarding claims data? All right. No. Okay. Then we'll move on. 네, 질문 없으시면 그냥 넘어갈게요, 이제. 네, 클레임스란 저번에 누가 저한테 물어보셔가지고 제가 한번 알아봤는데 공짜일 줄 알았더니 공짜가 아니네. 아, 근데 저건 공짜가 아니더라도 다른 게 공짜가 있어요. 보시면은. So even if the claims data themselves are not free, there are some free data. Okay, so now there's like COVID-19 hospital information. So this is free, 무료, free. There is also medication circulation information. Like, so pharmaceutical companies manufacture medications and then they push it into the market, and some people are interested in how the medications are circulated in the market, like which type of products are placed in which pharmacy or 이마트 or any some place, and they want to analyze like how much each product is sold in like which location. So some people are interested in that. Some diagnosis information, some meta information about how Korean government like classifies patients into different categories. So yeah, these are free. So these are all free. Not this one. Okay, so interesting stuff are usually not free. That's pretty unfortunate. What's happening here? Right. Disease information, pharmacy information, ICU admission statistics report. So these are like, all these are pretty high level information. They don't contain any personal health information, the PHI that I talked about last time. So these don't contain personal level information, which is why it's probably freely distributed. It usually, and it's the usual like analysis report on the very like high level, on a very high level, like which medications are sold where, like which hospital is packed with patients, and things like that. All right, then moving on. So machine learning for healthcare, the third material, the third slide there. So the recap, the last time the recap was how we get access to Mimic3. the basic structure of Mimic3, like admission patterns, like how there is like the hospital admission, and how there's within the hospital there's ICU admissions, and then there's tables, there's schemas, and the SQL queries, and also right now I just talked about the Korean National Insurance claims data. All right, so that was a recap. All right, moving on. So today's topic is I won't go. So because we've already spent like 30 minutes on the claims data and the recap, so I probably won't go into the actual prediction step, but I'll talk. So the overall overarching theme is the tasks. So we set the tasks for prediction, and then we pre-process data for doing the predict. All right. 혹시 저만 claims data 페이지가 보이나요? 정훈님 혹시 정훈님 혹시 지금 슬라이드 안 보이시나요? 아, 제가 화면 공유를 하지 않았나? 네, 누구는 보이시고, 제가 데스크탑 공유를 했기 때문에 다 보이셔야 될 텐데, 지금 요 슬라이드가. 아, 잠깐만, 렉처 넘버 2 슬라이드요? 렉처 넘버 3 슬라이드가 아니라? 지금 이 프리딕션의 today's topic 보이시나요, 다들? 안 보이시는 분 있나요? today's topic, simple prediction 안 보이시는 분? 이상하네. 제가 다시 화면 공유 다시 할게요. 네. 네, 혹시 지금 안 보이시는 분? today's topic, simple prediction 안 보이시는 분? 아, 예, 좋습니다. 네. Okay, so I guess everybody can see the slide where I say today's topic. Okay. So today's topic will be simple prediction, and so just to repeat myself. So so like we're given a task to do some predictions, so we will set the tasks. Well, I'll give you guys 2 examples, and then in order to do prediction, we need to pre-process the data, which is the mimic EHR, the raw data. So we need to convert the raw EHR into some like numerical form so that we can push that into the machine learning model. So we need to do data pre-processing, and I will just briefly talk about MapReduce in order. Like Mimic3 is not a big data. It only consists of like 50,000 ICU records or so. But like if you are working for like Naver or Google, then you like maybe you want to pre-process like millions of patient records spanning like I don't know what, like several terabytes of data. So in that case, you can't do it on a single machine in a single node. So you might want to do MapReduce, which is the big data, which is like a distributed data processing framework. So I'll talk about that briefly, and then if we have time today, then we can touch the subject of modeling, the classical approach and the deep learning approach. And there's not that much difference between classical approach and deep learning approach in terms of how we treat data. It's just that one requires a lot of feature engineering, the other, the deep learning, not so much. But it's you still need to decide which information you need. So okay, yeah, it'll be clear. It'll be more clearer to you guys once we go over the data pre-processing and see how we can have different approach when we use classical approach and deep learning approach. All right. Okay, so tasks. So today we'll talk about 2 tasks, which is hospital readmission prediction, and the second is ICU readmission prediction. All right, so I just want to make it clear that these 2 are not the same. So in the previous slide, I told you, I do have a slide here. So previously I told you that there's hospital admission and there's ICU admission. So readmission prediction can happen in 2 different levels. I didn't put mortality prediction here because I thought This would be more like technically more enlightening, I guess. All right. So task 1, hospital readmission prediction. The goal of this is that given the current hospital visit, predict whether the patient will return to the hospital again in 30 days. So if some of you remember, I said that the readmission prediction usually predicts whether the patient will return to the hospital in a short time frame for the same symptom or same disease, but not necessarily all the time. Like some hospitals just want to make sure that the patient doesn't come back to the hospital for any kind of reason within like short time frame. So this is what we'll do today. Given the current visit, predict whether the patient will return to the hospital again in 30 days. So 30 days, that's the time frame. And there's something called inclusion or exclusion criteria. So when we conduct a clinical research or medical research, we first have to construct a cohort being like a group of patients. So like so basically it defines a criteria for who are eligible to be included in this study. So the study here being the hospital readmission prediction, but it could be any study like clinical trials, like 임상실험, like where you try a new drug that hasn't been placed in the market yet. That's also a study, and there's like a lot of different kinds of study in a clinical domain. So, and every time you conduct a study or research, you have to recruit patients who are eligible for that study. Like if you're doing a clinical trial, like if you're doing a clinical trial, then you want to select a patient who actually has that disease, and like in a very there's a bunch of different criteria here. Typically the criteria consists of age, sex, condition being like what kind of like symptoms or disease you have, the medications that you took, the procedures that you have gone through, and they are usually established by medical experts. Like machine learning engineers or data scientists like ourselves, we don't really know what the actual consequence or the meaning of the clinical trials or the studies. So these criteria are set by the medical experts, usually doctors or biostatisticians or epidemiologists or like government, like I don't know, like 심평원 원장님, like some people who want to do like policy type of thing. So just to repeat in Korean, because this is kind of important. So just to repeat in Korean, 그 임상 실험을 할 때 보통 예를 들어서 암 임상 실험, 폐암 임상 실험이다 그러면 이제 뭐 폐암에 드는 약을 이제 신약을 개발해가지고 임상 실험 뭐 1상, 2상, 3상 뭐 이렇게 하잖아요. 이제 그거를 실제로 이 정부 승인을 받기 전에. 그럼 이제 1상이든 2상이든 3상이든 간에 임상 실험을 할 때 이제 뭐 폐암 신약이다 그러면 일단 폐암에 걸린 사람을 뽑아야겠죠. 그 다음에 폐암 걸린 사람 중에 기존에 다른 약을 이미 먹어본 사람은 또 뽑으면 안 되잖아요. 왜냐면 이제 그게 또 어떤 영향을 미칠지 모르니까 이 약에 대해서만 트라이를 해보고 싶은 거니까 이제 기존에 뭐 다른 약을 먹은 사람은 안 된다던가, 뭐 나이가 너무 많으면 안 된다던가, 뭐 다른 뭐 복합 병세가 뭐 어떤 복합증이 있다면 안 되던가, 뭐 이런 굉장히 다양한 그런 기준 어떤 이 컨디션들이 있거든요. 그거를 이제 이 임상 실험을 해서 이 약이 정말로 드는 약인지 안 드는 약인지를 이 통계적으로 분석을 하려면은 그런 어떤 여러 피처들을 잘 구분을 해가지고 이제 임상 실험을 진행을 해야 되는데, 그런 걸 우리 같은 머신러닝 하는 사람들이나 뭐 무슨 데이터 사이언티스트는 모르니까 이제 실제로 신약을 개발하는 사람들 또는 의사들이 이제 요런 환자는 넣어도 되고 요런 환자는 넣으면 안 된다 이런 거를 기준을 세워주거든요. 그럼 이제 그 기준을 저희 같은 머신러닝 하나 데이터 사이언티스트들이 그 기준 그대로 그냥 다 프로그램 짜가지고 이제 이 데이터베이스에서 또 사람들을 이렇게 다 환자들 추출을 한 겁니다. 이 기준에 맞는 환자는 넣고 기준에 안 맞는 환자는 버리고 이런 식으로. 네, 그렇게 됩니다. 그래서 뭐 저희가 근데 이제 오늘 하는 hospital readmission task 같은 경우는 뭐 이게 무슨 임상 실험이나 이런 굉장히 뭐 크리티컬한 태스크가 아니기 때문에, 크리티컬한 스터디가 아니기 때문에 저희는 뭐 딱히 이런 뭐 크라이테리아 없고 그냥 다 넣는 걸로 하겠습니다. 그냥 환자들. 그래서 영어로 So to speak in English, these inclusion exclusion criteria are very important in like highly like critical studies like randomized clinical trials for like new drugs. But today this is just all theoretical. This is just like a practice, and so we will just there is no criteria for today. We'll just include all the patients in Mimic3 to conduct this hospital readmission prediction task. All right, so I'll just go through a bunch of examples to give you guys an idea who are eligible, who are the positive samples and who are the negative samples. So, okay, just to recap, so the blue line, the blue bracket here, the blue bar, the strip is the hospital admission. The red strip is the ICU admission. So in this case, so based on this information, so the goal was that given the hospital visit, it's not given the ICU visit, it's given the current hospital visit. So given the hospital visit, based on this information, this blue strip, will this patient visit the hospital again? Okay, so yeah, will this patient visit the hospital again in 30 days? Well, I should have said 30 days, in 30 days. And the answer is, of course, no, because there's no blue strip here or in the future. So the answer is no. So example 1, no. And example 2, based on this information, will this patient visit the hospital again in 30 days? And in this case, there is another blue strip in the future, and the gap between these two hospital visits is what? It's like 13 days. So this meets the criteria for hospital readmission. So this is a yes. And example 3. So the difference between example 2 and 3 is that in this case, there are 2 ICU admissions in this hospital admission. This blue strip contains 2 red strips. But that doesn't really matter, right? Because it doesn't really matter whether how many ICU admissions there are in this visit. All we care about is that given 1 blue strip, will there be another blue strip in 30 days? And in this case, the gap between the 2 blue strips is what? It's more than a month. It's about 43 days or so. So this answer would be no. All right. Example, is there? Yeah, okay. Example 4. And so far, the patients only had 1 strip or 2 blue strips, meaning 1 hospital admission or 2 hospital admissions. But in this case, this patient has 3 hospital admissions. So 1 and 2 and 3. And so in this case, we have 3 samples. So because this is a hospital readmission prediction task. So each hospital admission becomes a sample, because each hospital admission, based on that, we can predict whether there will be another hospital admission in the future in 30 days. So in this case, from this patient, we can have 3 training samples, 1 and 2 and 3. And in this case, will this training sample be a positive training sample or a negative training sample? And because the gap is wider than a month here, so for this, the answer is no. So this training sample is a negative training sample. This one does have a blue strip in the future, and the gap is only 19 days. So for this is a positive training sample. And do I have another? Okay, so I don't have a slide for this part, but this becomes a negative training sample because this is the last hospital admission for this patient. There's no future hospital admission. So for this will be a negative training sample. Technically, to be really precise, we don't really know if there is a blue strip in the future or not. It's just that the Mimic3 EHR dataset only contains this much information, like this much, and we don't know anything in the future. So technically, we should filter out the last one as a training, because in order for this blue strip to become a proper training sample, we need to know whether there is a future blue strip or not. But the timeline is cut here because Mimic3 only contains up to here, so we don't know if there's any future blue strip or not. So to be technically correct, we shouldn't treat this as a training sample. So this is what we call a right-censored data problem, which is like a whole different. So this is right censored, left censored. Like those terms come from survival analysis or clinical survival analysis prediction tasks, where you track the survival of the patient on a temporal line, and if the patient is like if the patient stops coming to the hospital, then we don't know what happened to the patient. So that becomes like a right censored patient. So that is like a whole, there's like a lot of theories and techniques to deal with that. But today we won't go into detail. We won't do any of that. And we'll just treat this as a negative training sample. This blue strip will be just a negative training sample, but to be really correct, we should filter them out. All right. All right, moving on. So far, any questions so far with respect to the readmission label, which becomes positive, which becomes negative? Is there any question? No? Okay, then moving on. All right. Okay, so that was all about which is like positive sample and which is a negative sample. And technically, so the goal was that given the current hospital visit, predict the future hospital visit. But to be really, really correct, we should not try to okay, there's a chat here. So we're gonna treat the last sample as negative sample. Yes, yeah. I mean, I'll make it crystal clear how we should pre-process. When I give you guys homeworks for pre-processing the EHR, I'll make it clear like which becomes negative, which becomes positive. Okay, so to be really correct, let's just say that for homeworks, the last sample will be filtered out. So okay. So for consistency, from here now on, all the last samples will not be included in the training set. We'll just filter them out, and which will still be the same for the homeworks. And I'll make it clear that I'll put it in the specifications of the homework to describe that like I did today. All right. Okay. So all right. So just another technicality. So the setting is that we want to predict whether this happens in 30 days given this, but which is not really realistic, because in order to predict this event, whether the patient will come back to the hospital in 30 days, in order to predict this precise moment, we should probably use all the things that happened in the past, like all the medical experience that the patient has gone through, not just this alone, because we never know whether like there could be a dependency between this event and like something that happened here. We really don't know. I mean, intuitively we just think that something might have gone wrong here, so that's why this happens. But in a mathematical sense, to be really correct and rigorous, there's no way to really confirm that like something that happened here might have affected this event. So there could be dependencies coming from all past information. So to be really correct, we should use all the information in the past, not just this one, because dependency from all previous records. But I mean, the question still remains, like how much previous, like how far, like how old you want, how far you want to go back into the past. Like a 30-day readmission prediction probably doesn't depend on something that happened like 5 years ago. Like that's just too much. But it might but like, for example, if this happened like 6 months ago, this happened like 1 month ago, then maybe something that happened 6 months ago have affected this. So it's really hard to really tell like which information is relevant or which is not. But so there's we should make like a judgment call. Like I mean, we can't make that call because we're not doctors. We don't have any clinical medical expertise, so we can't say that. But doctors have a pretty good idea like how much far we need to go back in order to predict readmission. So we should always consult the doctors if you want to be really, if you want to build a product quality predictive models, then we should always consult the doctor. But for writing academic papers or doing like projects or homeworks, we don't need to talk to doctors. All right, so another thing is, please note that I didn't do this. I did this. This is because to make a meaningful predictive model, we should leave a room or some time to take actions, because if this happens, it means that this happened because something has gone wrong somewhere, like in here. And if we use all the information up to here, then that means that we don't leave any rooms for like improvements or like intervention. Like if what the realistic scenario is, at some point during the hospital admission, we want to run this predictive model to see if the patient will come back to the hospital within 30 days. At some point during the hospital, during the admission, and then if the model says very likely, like high risk readmission, high risk readmission patient, then we want to do something differently from within this time frame. Like if you run a predictive model at this point and then it says highly likely, then we want to do something different here. So just we want to leave a room for making some changes to what we do to the patient in order to prevent this from happening. But if we use all the time, if we run the model basically here, that doesn't really help you, because we can't do anything different. Like if we run the model at the moment of discharge, like what are we gonna do? So I hope that makes sense. So in order to make a really like a model that can be deployed in actual like clinical setting or clinical practice, we should like consider a lot of different aspects, like how much information that we want to use, and like at which point we want to make the prediction, and something like that. There's a lot of things to consider. Okay, so all right, let's move on to task 2 if there is no question. Task 2 is ICU readmission. So this is the second example, which is a different task than hospital readmission. So this is ICU readmission. All right. So the goal is, given the current ICU admission, not hospital, but ICU admission, predict whether the patient will return to the ICU. So like you can, there will be examples. So we'll predict whether the patient will return to the ICU within the same hospital stay, within the same blue strip. So here. So the setting is based on this information, based on this red strip, the red strip being the ICU stay. Based on this information, did this patient revisit ICU within the same hospital stay? So within the same blue strip, was there another red strip? And of course, the answer is no, because there's no red. There's only one red strip in the blue strip. So the answer is no. Now, another example. Based on this information, did the patient revisit? Will the patient revisit the ICU within the same hospital? So there is another red strip after this one, within the same blue strip. So the answer is yes, because according to the definition of the goal, we don't really care about the gap between the red strips. Like this usually like happens within like a couple days, because this is the same hospital stay. So the gap is typically not that wide. So we don't really care about the gap between the red strips. As long as the patient is readmitted back to the ICU, then that's a positive example. All right. Oh, and like before, as long as like there are the same number of training sample as the number of red strips. So for this red strip, the answer is yes. For this red strip, there is no more red strips in here. The red strip ends here, and then the patient is discharged from the hospital. So in this case, this is a no. And then another example. So maybe this patient has two hospital admissions, and each containing one ICU. So in this case, this is of course a no, because there is no red strip here. And okay, so there's no. In this case, this is also a no, of course. And so this patient has three ICU admissions, ICU stays within the same hospital admission. So 1 blue strip, 3 red strips. In this case, this is of course a yes. This is another yes. This is so this is another This is another yes. And this, okay. So the difference between the hospital and the ICU admission prediction task is that before we decided that we're not going to use this as a training sample because we don't know what happened here. But this ICU admission, we can use this as a training sample because we always know the end when the hospital admission ends. So we don't really care what happened here because the goal description is that we want to predict whether there is another red strip after this red strip, and until like how many red strips, basically how many red strips there are in the blue strip. So we don't really care what happens here after the hospital admission. As long as there's red strips here in a single blue strip, then they all qualify as a training sample. So you can see the difference. You can see the difference between the hospital admission task and ICU admission task. So, all right. And the same rule applies. In reality, to be really correct, in order to predict this event, the readmission, ICU readmission, we probably need all the information that happened. So we don't want to base our prediction for this only on this, because something might have happened, maybe something might have happened here, maybe something happened, maybe something might have happened in this blue strip or in this blue strip. Like anything could have happened that might affect this. So technically, to be really correct, we don't want to base our prediction solely on this red strip. Like we want to, because the same question, like dependency from all previous records. But like if we want to, let's say no, this is not okay. So this patient could have another blue strip before this blue strip. Like there could be a blue strip here. Like I can annotate, right? Draw like there could be a blue strip here. Okay, this is a wrong color. Right, so there could be a blue strip here that happened before this blue strip, and in order to predict this, maybe something have happened here to affect this, which is kind of unlikely, but we never know because we're not medical experts. We can't really tell like how much we want to go back into the past to predict this, but it is technically possible that something have happened here that affect this, not just here. So you never know. So, all right, and again, we want to leave a certain like amount of room for making changes to what we do in the ICU to prevent this from happening. So we want to like, but again, the question is how much time we want to leave. Like, do we want to make our predictions here or here or here or here or like here? It doesn't really like. There's an infinite number of possibilities, and usually it depends on the doctors or the hospital administrators, like when they want to make a prediction, or maybe they want to make a continuous prediction. Like they want to make a prediction every hour, like here, up until like some point, and then like like there could be like a million different ways of actually implementing this predictive model when you want to deploy this into the actual ICU setting. So like making money out of predictive model is really like it's really a difficult job. All right. Okay, moving on. So next is data preprocessing. So okay, so before we move on, any questions so far? 넘어가기 전에 혹시 뭐 아무거나 질문 있으시면 해주시면 되겠습니다. 혼자 떠들 때 엄청 힘드네요. All right. 네, 질문 없으시면, 네, if there is a question, we'll move on to data preprocessing. So yeah, it consists of two parts: workflow examples and MapReduce. So workflow examples, there will be two examples because we have two tasks, which is hospital readmission prediction. The other is ICU readmission prediction. So I will give you two workflow examples each for one task, and then we'll jump into MapReduce. All right, so data preprocessing really depends on the information you want to use, like, because there are a lot of information in the EHR. There are a lot of tables, a lot of different features, a lot of different variety of information. So you have to decide which you want to use. And then it also depends on like what kind of model you want to use. Like if you want to use logistic regression, or if you want to use RNN or transformer or CNN or whatever. So the way you want, how you pre-process data really depends on these two factors. But the modeling will come after the day. I have prepared the material so that the modeling comes after the pre-processing. So I'll just focus more on the information side rather than the model side on like making decisions on how you pre-process your data. All right, so hospital readmission. So this is what we want to do so the ideal situation was that we use like a lot of past information, and we want to like make the prediction at the certain like midpoint of the hospital stay. But just to make things simpler and to make the explanation easier, I'll just stick to the more naive, straightforward approach like this. Like based on this information, will this patient visit the hospital again? So we need to first we need to like go over all the patient. We need to go over all the tables in the EHR, the Mimic3, and then we need to extract patient records so that we can have like blue strips on a timeline, so that we can like figure out which is a positive sample and which is negative sample. So that's what we're gonna do. So we need to identify each hospital admissions, and we need to identify if they are positive samples or negative samples. So, all right. So if anybody remembers this, I showed you guys this picture from like the previous class, or previous class. So there are 25 or 25 tables in Mimic, and some tables are related to the hospital admission. Some tables are related to the ICU admission, ICU stays, and there are some meta information table, the definition tables. So technically, if we want to base our prediction on the information from here, so technically we should use all the tables, like all 25 tables, to construct our feature vector or our input to the machine learning model. Well, we can't do that. But this is just there are a lot of like garbage information, and we really don't know which information is garbage and which are not. And so we'll just stick to the obvious ones, which is these 1, 2, 3, 4, 5, these 5. So there are admission tables. So we'll just stick to 5 tables. Admission table, which gives you like all the information about the admission itself, and the diagnoses table, which diagnosis, the disease. Basically, you can equate the diagnosis to disease. So this is the disease table. The patient table, because we need to know like the information about the patient as well. The prescriptions table, which is the drugs. So this is the drug table. Procedure table is the procedure being like the SWEC, the IV fluid, or X-rays or MRIs, 심전도, EKGs, and lab tests like blood pressure, urine samples, and all that. So that becomes your procedures. So they're like the 3 like pillars of EHR. There's disease, there's medication, the drugs, and there's procedure. And then there are like different like side information, like the actual like lab events, which is like if you do like a lab test like blood pressure, then the results of taking the blood pressure should be recorded here. And like microbiology test, like if you take a human cell sample, 생검, and you culture it in a petri dish, and then you like analyze the thing that you grew in the petri dish. That becomes your microbiology test event. But we'll just stick to the high level information, like what kind of disease you had, what kind of drugs you took, and what kind of procedures you have gone through as a patient during this blue strip. And we won't use any of these like ICU related stuff, which is a bad idea to be correct. But it will, just to make things simple, we'll just stick to the high level information. All right, so we'll just go one table by one table to see, because each table consists of a lot of features, a lot of like columns. So we need to focus on like certain number of columns to construct your feature vector. So we'll start with the admissions table. So admissions table, there are a lot of like columns, but basically what you want to do is construct a dictionary. So I'm using like Python example. So Python, you want to do a Python dictionary of patients. So there are, because the most high level information in EHR is always the patient themselves, because the patient goes to a hospital creating admissions, and then there will be a lot of like information dangling like below the admission. So yeah, like here, like there's the patient becomes a timeline, the most high level information, and on the timeline on the patient, there will be like blue strips, and then in the blue strip there will be red strips, and then there will be like patient number 1, patient 2, patient 3, patient 4, patient 5, each having its own timeline. So first we need to have the patient level dictionary, and then the patient dictionary will consist of like different subject IDs. Subject ID is the unique identifiers given to each patient. Like John becomes like 1, 2, 3. The Mary becomes 4, 5, 6, and something like that. So subject ID becomes the primary key, and then HADM ID. This is the hospital admission ID. So each time the patient visits the hospital, that becomes another unique identifier. So each subject also has a dictionary again. So, and that dictionary will become like admission dictionary. So the patient, let me see. So I'll just copy paste this and this here. So there will be patient number 2, patient 3, like this, patient 2, and then there's patient 3. So we want to have a very high level like dictionary. Let me do an annotation here. So we want to have a very high level dictionary which contains these, and this becomes the key. And each patient has like different number of admissions. So within each patient, we want to have another dictionary that consists of like these information, the admissions themselves, and the keys will be the admission keys, the admission IDs. Clear. All right, so that's why we have like a double nested dictionary. I mean, this is just my implementation. You can do whatever you want. You can do as you see fit, but I found it most intuitive to have like a dictionary of dictionary. And so the innermost value of the nested dictionary will be the admission themselves. So we want to contain a lot of information about the admission. So we want to have the admission time, when this subject at this admission was admitted, when this patient at this admission visited the hospital, when they were discharged, the admission type, like whether it was an emergency room or the patient just walked into the hospital. The marital status. I don't know why marital status is part of the admissions, not the patient table, but still, like, I don't know. So marital status is whether you're married or like whether you're divorced or whether you're like single, like that kind of information. And I'm just including this information because I think there is a very, very slim, like, you never know if marital status will be like important information for predicting whether you will return to the hospital within 30 days. It's not likely, but I'm just giving you an example of what kind of information you can include in your data, in your training set. So this is your call, like whether you want to include marital status or not. It depends on you. Ethnicity. I mean, in Korea, we're all Koreans. It doesn't really matter. But in United States, like there are like Hispanics, there are like Black people, Asian people, white people, Hispanics, like Native Indians. So ethnicity is always one of the columns in the patient in your EHR. Again, I don't know why ethnicity is in the admission. Like your ethnicity doesn't really change admission by admission. It should be in the patient table, not the admissions table. But I don't know why it's here. Gender doesn't change. Like you don't become like men and well, maybe some people do it. Some people do. Okay. So gender, we'll just set this to 0 because you see that the admission type, marital status, ethnicity is all here, but the gender is in the patient table, which is weird. Like some information is in the admissions table, some information is in the patient's table. So it's just how things are in Mimic3. So we'll just set this to 0 for now because gender is binary information. It's either you're man or woman. These days there are like different types of gender, but in this like Mimic3, there's only men and women. So it's either 0 or 1. Admit diagnosis. So this diagnosis is different from this diagnosis. This is like a high-level description of why you were admitted, why you came to the hospital in the first place. So this is more like a general description of like you came because of chest pain, you came because of headache, like a very high-level information. So yeah. So admit we'll create a like a variable named admit diagnosis and fill it with this information. And then, as I said, there are 3 pillars. There's diagnoses, the disease, there's medications, the drugs, there's procedures, and there can be multiple number of diagnoses, medications, procedures per admission because you get a lot of drugs, you go through a lot of procedures, you get a lot of disease during a hospital stay. So we'll create a list for them and we'll populate them using other tables. And then the label itself to indicate whether this admission, this admission ID is a positive example or negative example. This will become our label, and we'll just set this to 0 for now because we need to know whether there will be another admission following this admission within 30 days. So we need to figure that out in the future, like in the later stages. So, all right. So admissions table, using this information, we can create this like nested dictionary. And then moving on, we can go to patient table and then we'll just match the subject ID to the subject ID here and then populate the gender for each admission. So each admission there was gender variable and we just set this to 0 for the time being. But now that we're in the patients table, we can populate them correctly. So there will be like a for loop, like for admission object in the patient's, this specific subject ID, we can just set all the gender feature to either 0, 0 being like male and 1 being female, or vice versa. It doesn't really matter. It depends on you. Diagnosis table is rather simple. It consists of only five columns, 5 features, and you can just use subject ID and admission ID to match this particular information to the nested dictionary that you created here. Here, you just put the subject ID, admission ID using these 2, and then set the and you populate the diagnosis list with this information, ICD code. And just to give you guys a small example. So the actual ICD looks like this. So the ICD code is it's a digit, but in this case, I don't know why, but they have they converted the numerical value to the string value. So this you can populate your diagnosis list with this string value. But the real actual ICD-9 code is something like 403.01. There will be like a decimal point somewhere. But we can care about that later. You can just populate them in this manner. You just copy paste. You just take this value, the varchar, and then convert it to a string, and then populate this list. And you can do the same for the procedures. The procedures ICD table is the same as the diagnosis ID table. It has the same schema, and then you can just match the subject ID, admission ID, and then populate the procedure list, not the diagnosis list, populate the procedure list with the ID here, which is also another like string value. Prescriptions are a bit different. Sometimes prescriptions do have ICU IDs. So prescriptions can happen anywhere between, it can happen anywhere. It could happen here in the blue region. It could happen in the red region. It could happen anywhere. So that's why it has way more like columns of features than these two. These two are mainly for like billing purposes. Billing mean like for reimbursement, the claims purposes. But this is more like a record saving purposes. So basically, it has subject ID and admission ID, but sometimes it has an ICU ID. So whether this some medication was prescribed or taken during the ICU admission, but it's not always. But sometimes it has null values because it was taken outside the ICU admission. So we're not going to use this information. We're not going to use this. We'll just take like basically three information from here, three information from here, again, three information from which is subject ID, admission ID, and the drug code themselves. So you can match the subject, admission ID, and then you populate the RX list with a drug code. Or there are a lot of different drug codes. Like there's drug name, drug CD, GSN, NDC. These are like all different versions of drug codes. So if you look at the drug table, there are a lot of information here, and so how can I get rid? Okay, so okay, this is just all right. So drugs. So there was drug name, generic form, CD, GSN, NDC. These are like different versions of drugs. So drug is like the very high level description of the ingredients of drug, like warfarin, heparin, I think there was like hydrochloroquine, or like different types of different like basic drug name. And then there's like GSN, and NDC is very it's a commonly used drug description in the United States. So this is typically NDC. It has like 11 digits or 10-digit number, and like first four digit is like the label. It's like the company name, and then the next 3 digit is like the ingredient name, and the last 4 digit is the package name. So like a lot of people use NDC, but for our purposes, for predicting whether the patient will be readmitted to the hospital, I think just using this like high level drug is probably enough. Or if you're interested, you could use this, which is a drug CD. It consists of like the ingredient name and the dosage of the drug, because there's like dosage number here. Like you can take heparin in 250 milliliters, or you can take warfarin with like 2 milligram tablets. And typically these formularly drug CD contains both the ingredients and the actual ingredient, like warf 2 or warf 0, or like tacrolimus, like 5 milligram capsule, then tacro 5, something like that. So it's a bit more like granular information compared to this information. All right, so you can either take this or this, and then start populating the RX list. So you do that. So basically, after you've done this, then you have populated all the information here. You've done this, and you've done these. All you need to do is just set the labels to like positive example or negative example. So in order to do that, you need to sort your admissions by the time, the admission time. So here, so far we just had like the nested dictionary. So the admissions themselves were like just it was unordered basically, but you want to order them by their admission time, so that you can okay, yeah, basically you can have right. So you want to order them like here, instead of putting them in a dictionary, you need to have like a list, like an ordered list, and then you need to decide whether this gap is 30 days and whether this gap is 30 days. In order to set this as a positive example and set this as a positive example, well, we're gonna of course remove the last one. So in order to do this, we need to sort the admissions in the dictionary by the time by the admission time. So I'm just gonna give you like a code snippet on how to do that. So basically, what we have is here is this, like all the admissions per patient lives in the dictionary, and you want to sort them by the patient, the subject ID, admission ID, the admit time themselves. And you can do this by like doing like a sorted, like inline sorting command, execution command. And then you can use this list to iterate through the actual dictionary, and then in the temporal order, and set the labels to 1 if the gap between the current item and the next is less than or equal to 30 days. So you get the idea. So the final output would be a list of admission objects, regardless. So before we had like a patient's, we had a patient dictionary where each patient consists of different admission objects. But as the final output, before we put them into the model, we want to forget about the patient IDs, because we're going to treat each admission as an independent training sample. So we'll just forget about the patient ID and we go through all the admissions. We go through all the patient. I think it's better to have a yeah, we want to take like here. So if we have a dictionary of keys and values, we just want to strip all the admissions, like here, take this, take this, take this, and take this, and then put them into a very long list. Like there will be admission 1, admission 2, like different number of admissions, admissions, and each admission will be labeled either positive or negative. And then once you have this, then you can like split them into a training sample, validation sample, and test sample to do like an n-fold cross validation. We'll talk about it in the modeling side. All right. All right, so far, any question? 아니면 뭐 한글로 제가 다시 설명해 드려야 될 부분이 있을까요? No? All right. Okay. Okay, it's okay. All right, the second one, okay, we only have 10 minutes, so I guess we probably don't have time to go into MapReduce, which is a bit more interesting, but I won't give you guys any homeworks for doing MapReduce because it's just a lot of engineering. But this, I guess, yeah, we'll pick up from MapReduce in the next class. Today we'll just wrap up with another task, which is IC readmission. So in order to do data pre-processing for IC readmission, just to recap, we want to use this information to predict whether there will be another red strip within the same blue strip. So moving on to the tables. Reasonably, we only want to use information within this red strip, which is these tables, and particularly among all the tables for the red strip, we're going to just use 2 things. I mean, you can still use like information from here. Like you can still use the ethnicity, the gender, the marital status to predict whether whether there will be another red strip after this one. But we like, just for the sake of showing, like demonstrating the pre-processing example, I won't use any of the tables related to the entire hospital admission, the blue strip. So I'm just gonna use these 2 tables, and it probably is not that much of a big deal, because this, I'm not sure if you guys remember, but among like among like 40 something gigabytes of the entire Mimic3 EHR dataset, 36 gigabytes. This takes up 36 gigabytes, this chart events. So like most of the information resides within this table, and all the other tables are mostly just meta level or high level descriptions. So I think using this only is not that bad of an idea. So, and ICU stays is exactly like the admissions. Like you need to know when the ICU stay started and when it ended in order to like sort them by timeline. Just like you sorted the blue strips by their admission time, you need to sort the red lines within the blue strip. I mean, you need to sort the red strips within the blue strip in a temporal order to see if there is another readmission. So we need to do that using the meta information from here, and they will populate, like just like we populated diagnosis and medications procedure, we're going to populate the information related to the ICU using this table. All right. So moving on to the ICU stays. So we no longer care about the patient because the patient information is no longer relevant because we're going to treat each ICU stay as an independent sample, and we only need to the reason we need the admission ID is because we want to sort the individual ICU stays in a temporal order, and in order to do that, we need to merge them by the same admission ID. So the subject ID is no longer relevant. So we're not gonna do that. But in the similar spirit as in the previous example, in the similar spirit, we're going to use doubly nested dictionaries. So the first level dictionary is the hospital stay, the hospital admission themselves, and then the inner level dictionary will be the ICU stay. So just like before, there was patient level and the admission level, like hospital admission level. Now we're moving on to ICU. So we're moving like one step below. So there will be the first layer will be no longer patient, it'll be hospital admission, and the second layer will be ICU admission. So it's again nested dictionary. And then there will be in time and out time, just like there was there was admission time and discharge time. There will be in time and out time, which is when you enter the ICU, when you go out of the ICU. Length of stay, just using this because this might be relevant for predicting whether this patient will be readmitted to the ICU. And then chart items and chart values will be like the diagnosis and medication procedures. So the items will be the items themselves, because like chart items consist of a lot of stuff, like your blood pressure, your O2 saturation, your temperature, and all kinds of like things that you measure when you're in the ICU bed. So like what you measured will be the items, and the actual value of the measurement will be in the values. So it'll be like a paired list. So these will come from the chart events table, and the labels will just set them to 0 for now. We'll need to sort them by like in time again, just like we did for the admissions. So, and then moving on to the chart events. So chart events it has a lot of things, but basically we want to take 4 things. So admission ID and ICU ID, we need these 2 because we need to map them into the nested dictionary. So we map HAdmin ID here and ICU admin here. And there were 2 lists, the items list and the values list. So the items list will be populated with the item ID, which is basically a number. If you use this, sorry. So item ID is basically just a bunch of numbers, like numbers here, like 20823, like 17525, like they're like a bunch of numbers, and they can, if you are interested in the identity of these numbers, like 17525, you can go to item ID dictionary. What was 17252? Oh, what was it? 17525? Sorry, I forgot. 17525. All right. 17525. That's weird. Why isn't there chart item and chart time? CGID value. Oh, I'm sorry. The item ID comes from here. So row ID, subject ID, admission ID, IC stay ID, item ID. All right, like if you want to look them up, like this becomes inspired O2 fraction. I don't want that. I have no idea what this is, but this is some measurement that you take when you're in the ICU bed. So anyway, so you take the item ID, you populate them, and then the value number, again, there are values associated with the item. So the values will be like 58. I mean, there's value and there's value number. And if the value is a number, then it'll be mapped to the numbers. Like this is a string and this is this is number. So we'll just take the items that has the numerical value. Sometimes there will be like none or like outlier or like anomaly. Like there will be string values, but we won't take them. We'll just take the values that has actual numerical values. So we'll just take them and then populate them with in the chart values. All right. So we do this. So we go through the chart events and then we populate these. So now that we do that, we have populated these. So we just need to do this, and which is in the same manner. We just sort the ICU stays by in time, and you can do that. And then so you have like a sorted ICU list, and then you can use that sorted ICU list to see if each ICU stay should be like a positive sample or a negative sample, depending on whether there is another red strip after the current red strip. So you do that. And the final outcome will be just like the final outcome of the previous task. This will be a list of ICU objects. So we no longer care about like, well, I mean, we didn't care about the patient ID from the beginning, but we no longer care about the hospital admission themselves. We strip the blue red strip, we strip the red blue strip totally away, and then just we populate a single list with a different bunch of red strips, which each of them annotated like either positive or negative. So that'll be your final outcome, and then you can, again, in the same manner, you can split them into like train validation tests to do n-fold cross validation. All right, so I think our time's up. So just very quickly, if there's is there any question related to like anything that I talked about today? No? All right, all right, next time we'll start with the MapReduce, so I'll just stop sharing. All right. Okay, so if you have any question, or I mean, if you think about anything, just put them on the classroom. I'll read them, and then please download the Dropbox link and then decompress them, and then try to take a look. Just basically, they're just a bunch of tables, and then if you have any trouble doing that, also send an email to me or put them on class. Post a message on Classroom. I'll try to take care of it, and then hopefully by the next class, everybody will have their have the EHR, Mimic3 EHR on their local disks. All right, thank you very much. Bye-bye. Thank you very much, people. Have a nice weekend. I'll see you guys next Tuesday. Bye-bye. 민기님, 용식님, 그 혹시 제가 보니까 중간에 그 두 분 정도 더 들어오셨던 것 같은데 그거 혹시 체크하셨나요? 누가 들어오셨는지?
아, 네, 아까 체크했습니다.
아, 예, 학생분들 들어오신 건가요? 그러면은?
그 네이버 분 한 분 들어오셨고요.
네네.
아, 네이버가 아니라 라인 분 한 분 들어오셨고요.
아, 네.
그리고 그 미카엘 폴리 학생이 미카엘 폴리 학생이 아니고 잠시만요. 중간에 맞는 것 같습니다. 미카엘 폴리 학생이 좀 늦게 들어왔습니다.
아, 예. 오늘 김지성님은 안 들어오셨나 보네.
네.
예, 알겠습니다. 예, 뭐 미리 또 알아서 체크해 주셔서 또 감사합니다.
아닙니다.
네, 그럼 수고하셨고요. 또 뭐 클래스홈에 올라오거나 이러면 또 시간 되시면 한번 체크 좀 해주세요.
네, 알겠습니다, 교수님.
네, 감사합니다.
감사합니다.
네.